All right. So yesterday we talked about single replacement reactions. Wednesday we talked about the first step. Yesterday we talked about the other 4 steps. So what I want to do is show you a couple of problems on the worksheet. So we might as well go ahead and do, I want to do number 2 real quick and at least 3 and see what we get to after that. But 2, barium nitrate and zinc. So barium is Ba, has a charge of +2. Nitrate is NO3 with a -1 charge. So barium nitrate is going to be Ba, NO3, 2. And we said earlier this week that compounds in a single replacement reaction are aqueous. We're going to react that with zinc metal. And remember, metals are monatomic, meaning no subscript, and neutral, meaning no charge in the top right corner. And we said that metals are solids. So now we have to determine if a reaction takes place. We know that a reaction takes place if the metal by itself is higher on the activity series than the metal in the compound. So we need to see if Zn is higher on the activity series blue sheet of Ba. And it actually is not. Zn is lower on the activity series than Ba. So life is really easy. You don't have anything to do for this reaction. All you have to do is put non-reaction. It simply will not work. If you put zinc metal into a solution of barium nitrate, it won't do anything. So then the next problem, number 3, does work. Potassium metal plus 10 or nitrate. Potassium is the symbol K. It is a solid monatomic metal, neutral metal. And then 10-4, the 4 means that that's the charge on the 10. And 10 goes by the symbol Sn. So it's going to be Sn plus 4. And we saw nitrate on the green sheet is NO3 -1. So 10-4 nitrate is going to be Sn NO3 4. Now I said that you do have a reaction, and again that's because K is higher than Sn on the activity series. So we will have a reaction where 10 is displaced. So Sn is going to be kicked out of the compound. And it's a metal, so it's monatomic, meaning no subscript. It's a metal, so it's neutral, meaning no charge. And it's a solid. Now off to the side, we need to work out our charges for potassium nitrate because the K is going to be with the NO3. Now K is +1, NO3 is a -1. So it's not going to be KNO4, NO34, it's going to be KNO3. And it's a compound in a single replacement reaction. So it's aqueous. Now that's what we call the molecular equation. I'm going to abbreviate molecular equation ME. We need to balance it because a molecular equation always has the phases, and I noticed I forgot a phase. SnNO34, it's a compound in a single replacement reaction, so it's aqueous. So molecular equations have phases. That's one thing I'm looking for. I take off 1 point for each phase you miss. So you need your phases. You can't do the other steps without the phases. So what's the point of writing a molecular equation without the phase? You have to have a phase in order to do the next steps. And then it needs to be balanced. So I'm going to balance this 4 KNO3, and that makes me need 4 Ks in the reactants. So that's the molecular equation. Now, yesterday we learned how to do the complete ionic equation. One thing that's helpful for students is to circle the solids for the complete ionic equation. So we're going to circle the 4K solid and the SN solid. Now, what that tells me is that I just blindly copy what I circled down. Okay, just blindly copy it down. So we have the 4K solids. That's going to be blindly copied down. And solids are neutral. You will not put a charge on solids. You won't break it apart, no charge, nothing. Just copy it down blindly. Now with the aqueous, we are going to break it apart into its ions. Now Sn we said was a charge of a +4. Now with aqueous compounds, they're going to break into individual ions. Now, like I said yesterday, unless it's a polyatomic ion, you make your subscripts coefficients. You do have to pay attention to whether or not your polyatomic ion is in parentheses. If your polyatomic ion is in parentheses, you're going to keep that what's in parentheses. Outside of the parentheses becomes a coefficient. So you're going to make the outside of the parentheses a coefficient. So this NO34 is going to turn into 4 NO3 with its charge of -1. And that's aqueous. Then we get to SN solid. It's circled, so we're going to keep it SN solid. And then we get to 4 KNO3 aqueous. So we're going to break that apart. Now you have to pay attention to some balancing because the 4 refers to the K ions and the NO3 ions. So we've got 4 K+1 ions aqueous plus 4 NO3 -1 ions aqueous. And then that's all to the complete ionic equation. Now, the easiest of the 5 steps for single replacement reactions is the net ionic equation. Now, with the net ionic equation, we are going to cancel out what is the same on both sides. Everything about the things being the same on both sides. Everything that we cancel out, we call it what we cancel out, spectator ions. If it's a spectator ion, you have to have the same charge, the same phase, the same coefficient. Everything about what you cancel out spectator ions has to be exactly the same. I'll give you a hint. In metal single replacement, it's always the anion that is the spectator ion. The metals will never cancel out. If you cancel out a metal in a complete ionic equation, it's because you put charges where you shouldn't have. If you get everything to cancel out in the single replacement reaction, there's something wrong. But with metal replacement, it's the anion that gets canceled out. It's the anion that's the spectator. So the anion in this reaction is the 4 NO3, -1. So now the net ionic equations rewrite what we haven't canceled out. So we have 4K solid plus SN plus 4 aqueous yields SN solid plus 4K plus 1 aqueous. So that's a complete and net ionic equation. Now with single replacement, we do the redox, oxidation and reduction half reactions. So remember yesterday, the half reactions show you how many electrons are involved in the reaction. Now, the way I like to figure out what's been reduced first, and then by default, the other thing has been oxidized. But I do like to write the oxidation half reaction first. So reduced in chemistry means the same in everyday life. Price reduced means that price went down. In chemistry, if a species was reduced, that means the charge went down. For metal replacement, for reduction, for metal replacement, you're going to have a cation going to a neutral. So for reduction, for metal replacement, you're going to have something aqueous, cation, going to a solid neutral atom. So, and let's just make sure to take my word for it, not take my word for it. Sn plus 4 yields Sn solid neutral. So Sn plus 4 yields Sn 0. That was, in fact, the charge went down, so the Sn was reduced. That means the potassium must have been oxidized. Now, oxidized in chemistry is the opposite of reduction. Oxidation means the charge goes up. Now, for metal replacement, you're going to have the metal solid neutral yielding a cation for oxidation. So K0 yields K plus 1. The charge did go up. So the K was oxidized. Now I do like to write the oxidation half reaction first, because with oxidation, oxidation half reactions, your electrons are products, meaning they're on the right side of the arrow. So with oxidation, we pick out what charge has gone up, Now you're going to keep conservation of matter. One thing about half reactions, you conserve matter and you conserve charge. That means the same number of atoms or ions has to be the same on both sides. And the charge, the total net charge has to be the same on both sides. And so the oxidation half reaction, we said the 4K solid was oxidized. And that's going to yield 4K plus 1. Now remember, aqueous. Remember yesterday we said that electrons are symbolized by a lowercase e with a -1 charge. You cannot change that -1 charge. You can't take away electrons. All you can do is put electrons either as reactants or products. Oxidation are always products. So we're going to have 4K plus 1 plus a certain number of electrons. Now we're after total charge. We have to conserve total charge. So just like balancing, right? Subscripts and coefficients multiply your charges as well. So this 4 multiplies this plus 1. Okay, so we have a total of plus 4 with that potassium. We have 0, 4 times 0 is 0. So we have 0 in the reactants, but plus 4 in the products. So we need 4 electrons with a -1 charge to give us the -4 to balance out that positive. Now the reduction is nice and easy. The reduction, the reason why I like writing oxidation first is because however many electrons you figure out are produced in oxidation, that's how many electrons you need to react with your reactant in reduction. So, for example, Sn plus 4. Aqueous. Plus, you can blindly go ahead and put 4 electrons. Yields the Sn solid. Now, let's just make sure that our charges balanced out and equals 0. Plus 4 with the Sn plus 4. The 4 electrons yield a -4, and that yields something 0. Plus 4 -4 is 0 as well.